Hi class, today we're going to be looking at binary numbers in more detail. We're also going to be looking at how to do a little bit of binary math, some addition, some multiplication with binary numbers. Now, let's actually take a step back and think about how are numbers just represented in general, in the past or maybe long time ago. Perhaps we counted just by using sticks. And to represent the number 5, I had 5 sticks. Then, if I have 11, what do? I have 11 sticks. That's kind of a lot. So Roman numerals, they came up with another symbol to represent 10. So we put 10 here and a 1 to represent the number 11. But then what if we want to represent the number 100? We have to make another symbol, which they did, and so forth. It's actually quite hard to do math using either of these systems. 3 plus, what is this, 7 is equal to 10. And in Roman numeral kind of systems here, what does this add up to? I don't know. So we don't actually use any of those systems ourselves. We actually use what is called the place value system. And when we use the place value system, a number like this 5 here, that is in the second position here, actually has a value of 5 tens. This number 2 here, which is in the fourth position over, has a value of 2 thousands. And so we don't need, a different symbol for 1,000. We actually put the 2 here and move it over by 4 positions to give it the value of 2,000. Okay, so in this case here, 12059, we have 1 10,000, 2 thousands, 0 hundreds, 5 tens, and 9 ones. Okay, that's what we've been using all this time, and it might not have been kind of spelled out exactly that that's how we're doing it, but that's how this base 10 place value system works. Tens, hundreds, thousands, 10,000s. And so every place increases by a power of 10. We could do other place value, other bases as well in this place value system. I have 1s, 20s, 2 to the 20th. So, this would be 20 squared. This would be 20 cubed, and this would be 20 to the 4th. So 8,000 and 160,000. So the general concept is the same. I have 1 of these. I have 2 of these. I have 5 20s and 9 1s. And all together, if I add that all up, my value overall, in this case, is 176,000. So this number that looks like 12,000, if we are thinking decimal, it actually has a value of 176,000 things. Binary system is exactly the same. In this case, we only have 2 digits. We have a 0 or we have a 1. And each of the places are powers of 2. So we start with 1, then 2, then 4, 8, 16, 32. And down below it, the number can either be a 0 or it could be a 1. So in this case, I have 132, I have 1 8, 1 4, and 0 of everything else. So I just add up 32 plus 8 plus 4 So this number here, 101100, has a value of 45. Now, with other bases, with base 10, we have 10 different digits, 0, 1, 2, 3, 4, 5, 6, 7, 8, 9. With base 8, we only have 8 valid digits, 0 through 7. And with base 2, we only have 2 valid digits, a 0 or a 1. There is no such symbol for the number 2 or the value of 2. We have to actually go over by one place to represent the number 2 as a 1, 0, because there is no symbol of a 2 in base 2. Okay. Now, we have a notation that tells us what base we're kind of talking about. We use a subscript to indicate that base. So when I see 101 and a subscript of 2, I understand that as, I understand that as a base 2 value, which actually has a value of 5. 1 plus 4. Now, if I put a 10 down below, it's a base 10, and it's kind of what we understand and use every day. It has a value of 101. Now, the more digits I have, it makes sense that I have a bigger number. So if I have 4 digits in binary, I could have up to the value of 16, from 0 up to 15. If I have 8 digits, now I'm talking 2 to the 8th. I could have 256 values, 0 to 255. 16 digits, over 65,000, 2 to the 16th. And in general, with n digits, I could represent 2 to the n different values. And the reason I put this -1 here is because if I start from 0, then I go up to 2 to the nth minus 1. And that's assuming I start from the number 0. I could start from the number 1 and go up to the value of 2 to the nth if I wanted to just represent my numbers differently. Now, in general, we ignore leading 0. So whether it's written like this, or whether it's written like this, or like this, they are all to be interpreted the same way. We would never normally do that with decimal numbers. Like we wouldn't write 0, 5, 9, but you could. It's just not normal to do. But in binary, it's a little more typical that you will see leading zeros in a number, and you just ignore them. Okay, I want to practice here, and I'm going to maybe even pause for a little bit while you think about this and do this on your own. I want you to write out the values from 0 to 10 all in binary. And I started you out here. But notice here, and I'll kind of get you going a little bit more. I don't have a symbol of a 2, that there's no such thing as that. I filled up this position, and so I need to move over to the next spot and put a 1 there, and then make a 0 there, and then 0, 0. And now that I have an kind of this 0 in the 1's position, now I can turn that into a 1 to represent my 3. Okay, I'm going to pause right here, and I want you to do the rest. Okay, so pause your video right now, and I'm going to continue right now. Okay, so we could fill this out. This would be 4. This would be 5. This would be 6. We have 7. We have 8, 9, and 10. You should get good at this. Practice this, okay? How do I convert binary to decimal? If I have a number like this, 0, 1, 1, 0, 1, 1, 0, 1, what's the decimal value of that? So the table method, I'm going to show you a method here called the table method. I write the numbers of the place value right on top of it. And once I have that, I simply add up wherever I see a 1, I add those up. So I add 64 plus 32 plus 4 plus 1, and I get my value of 101. Let's go the other way now. Let's go from decimal to binary. So suppose I want to convert 83 to binary. What do I do? Well, I'm going to start off the same way with a table. And I'm going to think to myself, where should I put the 1? And I'm going to go with the biggest value first. I'm going to put a 1 on the 64. So I'm looking for the largest number smaller than 83. That's the 64. So I now have represented the value of 64. How much left do I need to represent? So I'm going to subtract 83 minus 16. I need to still make another 19. Okay, so I look back up here. I don't want to put a 1 here, but I will put a 1 under the 16. So now I subtract again, 19 minus 16. Now I only need to represent 3 more. So I don't want to put a 1 here, don't want to put a 1 here. I'm going to put a 1 right there. I now need to represent 1 more value, and I put 1 more remaining 1 over here to finish it off, and I'm done representing the number 83. This is the binary version. This is what's called the table method. Now, I do have another method that I want to show you, and I call it the division method. So let's take another number, 105. And I'm going to start by dividing it by 2. And I need to remember what the remainder is. So 105 divided by 2 is 52 with a remainder of 1. So I'm going to put a 1 here. This is kind of my, it's not my final answer, but it's kind of the answer that it will build up to be. Okay. I take the 52, divide that by 2, and I get a remainder of 0. So then I put that 0 onto the left side of my answer. And then I kind of keep repeating on this. I take 26 and I divide that by 2. And this remainder of 0 gets added to the left side here. And then I just repeat that again and again and again. So 13 divided by 2 has a remainder of 1. I put that 1 here. 6 divided by 2 has a remainder of 0. So I add that 0 here. 3 has a remainder, 3 divided by 2 has a remainder of 1. So I add that 1 right here. And then one more time, 1 divided by 2 is 0 with the remainder of 1. And I put that last and final 1 over here. And this is my final answer. And I stop here because, it doesn't make sense, to do 0 divided by 2. I could, I guess. I get 0 with the remainder of 0. And then I put a 0 in front of all of this. But at this point, I'm just adding extra leading zeros to the left. And at that point, it's kind of evident I should just stop. Okay, let's talk about doing some arithmetic now. And the nice thing about binary math is that it's really similar to the ideas of decimal math. So let's look at how I would add up a decimal number. In this case here, I'm going to add 8 plus 3, and I get 11. But because 11 is bigger than 9 in the decimal world, I need to carry over. And so I carry the 1 and I copy, the other one down here for a value of 11. Then I add up 1 plus 5 plus 6 and I get 12. Again, 12 is too big. So I need to carry over the 1 and leave the 2 down here. Then I add 1 plus 1 is 2 for my answer. Now, binary is the same concept, but the only difference now is I carry differently. I carry with any answer bigger than 1, because I can't represent 2 other than by having a higher place value. So 1 plus 1 here is 2, but I need to carry there. So I put a 1 up here and a 0 down here. This is the binary version of 2. Again, 1 plus 1 is 2. I need to carry again. 1 plus 1 plus 1 is 3. That's too big as well. I need to carry again. And this time I put a 1 up here and a 1 down here for the value 3. Then 1 plus 0 is 1. And this is my final answer. Now, it's a good thing to double check your work here. So I would go and kind of think to myself, okay, what is the decimal value of that? That's 7. The decimal value of this is 5. If I add those up, that's 12. And then if I take this and convert it, this has a place value of 8. This has a place value of 4. 8 plus 4 is 12. It checks out. They're the same. So that's good. Okay, that's addition. Let's look at one final thing. Oh, before we do that, there's this idea of hardware overflow. Sometimes in hardware, we only have a fixed size result. For example, maybe we have a 4-bit adder and we can only hold a 4-bit result. So in the case of adding this 4-bit number to this 4-bit number, I actually would need a 5th place value to hold the answer. 4 bits is not enough. 4 digits is not enough to specify the answer. And I say that we have what's called an overflow in that case. And it really is a hardware overflow. I mean, if I had a piece of paper, there's no limit to how much I can add an extra place value. In math, we never really use this term overflow. So if I had 999 and I added 1 to it, I get 1,000, and I never said that overflowed. I just added an extra place value to the left. And I could do the same with binary, but the thing is, in hardware, when I'm designing these adders, I have fixed sizes. And if I've designed it to be a 4-bit adder with a 4-bit result, I don't have a 5th bit. And in that case, I could come into a situation where I add up 2 numbers and the number becomes too big for 4 bits. And in that case, we have what's called an overflow situation. Okay, last thing we're going to look at is multiplication. Now, in multiplication, same thing. Let's look at how we do it with decimals. I take 158 and I multiply it by 3, and I get 474. Then when I multiply 1 times 158, I move it over. I shift it over in place by 1, and so I have 158 shifted over. And then once I've done that, I add straight down. 4, 7 plus 8 is 5, carry 1. This is 10, carry 1, and then my 2. Okay? Binary actually is multiplication in binary is actually even easier because we don't have to multiply by 3. I don't have to multiply by a big number like 7. Yuck. I just have to multiply by 0 or I multiply by 1. So 1 times this number up here, I basically just copy it down. 0 times this, that's easy. 1 times this again, it's just really copying it down and shifting it over. So now at this point, I need to add down. 0, bring that down. 1 plus 0 is 1. 1 plus 0 is 1. 0 plus 1 is 1. In this case, this example, there's no carrying involved. 1 plus 0 is 1. And this is my final answer. Let's do a sanity check. Let's actually double check that this is right. This has the value of 6. So this is 2, and this is 4. This has a value of 5, because this is 4, and this is 1. Let's see what this is. This has a value of 2, 4, 8, 16. I add up all these numbers together, and I get 30. And when I multiply 6 times 5, I get 30. They're the same. My work checks out. That's good. This is actually how I want you to check your answers and show your work on your little assignment that I'm going to be giving you. Okay, so that's the lesson for today. Hopefully you understand this new binary number system and how we can convert and how we can actually add and how we can multiply.